Let's talk about the Friday warm-up, which, cool, I have it right here. Thank you. Okay, so I gave that one back to y'all. So number one, the Friday warm-up, your function was e to the g of x, and I ultimately asked you for f prime of 3. And anytime you're evaluating a calculator, anytime you're evaluating a derivative, which we are here, I gave you a function and I said find f prime of 3, you have to find f prime in terms of x first. Write that down first. The only exception to that is if you have an explicit function, which this is not because we don't know what g of x is, and it's a calculator question. If it's a calculator question where you're expected to just use the derivative at a point command, you can do that, but this is not one of those. And even if this was a calculator question, you cannot punch e to the g of x in the calculator because we don't know what g is. So you would still have to find the derivative, and you should know that the derivative of e to a function is e to the function times the derivative of the function. That's what you should have written first. Now, I personally like to put the g prime in front. I would not have put it after, but whatever. Then we plug in 3. E to the f, or f prime of 3 would be e to the g of 3 times g prime of 3. And both of those values were given to you, and you just have to substitute them. So I think it was e to the negative 1. Or no, e to the 5th. G of 3 was 5. So it'd be e to the 5th times negative 1, and you can just stop there. You don't have to do anything with that. You could make it negative e to the 5th. You definitely don't want to try to get a decimal for that because you don't have a calculator. We good on that one? Good on that one. Those of you who messed it up, do we see where we messed up? And then number 2, anytime I see a limit of a fraction, I will default to my L'Hopital approach, and very few of you, I believe, very few of you actually went through and did the actual steps that you're supposed to go through with L'Hopital's rule. You need to get in the habit in a free response situation of evaluating top and bottom separately. If I plug in 0, e to the 0 is 1, cosine of 0 is 1, so my top is approaching 0. The natural log of 1 is 0. Now we do L'Hopital's rule. And L'Hopital's rule, once you know the top and bottom approach to 0 independently, says you do the derivative of top and bottom separately. The derivative of e to the 2x is the same formula we used in number 1, so that'd be 2 e to the 2x, if you forgot that 2. And the derivative of negative cosine x will be positive sine x over the derivative of the natural log of x plus 1 is 1 over x plus 1. And then when I plug in 0 for x, you get 2e to the 0, which is 2, plus sine of 0, all over 1 divided by 0 plus 1, which is 1. And so you should have had an answer of 2 for that one. We good? Cool. All right. So then I will check the ones you just did, and we'll go over that one tomorrow. I gave y'all as you came in. Oh, wait. Before we do that, I did tell you to watch a video for homework. Hopefully you watched that, because if you didn't, those of you who watched it, if people didn't watch it, do you think they're going to be able to just jump in and figure it out? It's in my opinion, it is the most cumbersome, labor-intensive crap we do all year. I think that's safe to say. We will do some things that may be more difficult conceptually, but the number of steps you have to do this stuff is a pain in the butt. So you were supposed to fill in all of this stuff for notes. That was what the video was. And then at the very bottom, there are actually 3. I want to only do the first 2. And they are cumbersome. See what you can do with those using the formulas that are on that sheet. If you didn't watch it, you need to watch that lesson at some point. Like, it's one of those that I'm not going to take the time to reteach. Some things are really quick and I can very quickly catch you up. This is not one of them. So if you didn't take the time to watch the lesson, you've got to do that. It's just not an intuitive thing. I don't know, whatever. Do you think you understood any of it? I don't know, maybe. All right, so see what you can do with those, and we'll compare our answers. I will also show you today, if you don't, how many of y'all do not know how to get exact areas through the antiderivative approach? Like, there's a way you can answer these questions with a very quick, nice process using antiderivatives. I'm going to talk to you about that today so you can check your answers very quickly. Just while I'm thinking about it, my original plan was to have a test next Thursday before Thanksgiving. That's not going to happen. I think we would have to go way too fast to cover the things I was going to put on the test. So we'll just kind of push that off later and see what happens with that. What we'll probably end up doing is just having one big test right before Christmas instead of breaking it up. Unless you want to test. Is everything okay? Why are you laughing at me? Okay. All right. See what y'all can do with this. Ugly? Yeah, these are. Something I think I pointed out to you a long time ago when it comes to limits. When you are solving limits, you need to get in the habit of continually writing limit as, in this case, n approaches infinity with each line of work until you actually evaluate the limit. I got a little bit lazy on this and I just did that little vertical bar thing just because I didn't want to write limit 12 times. But do know that on the AP exam, if it's a free response question, if you're doing limits, you need to write limit until you get to that final step where you actually write what it equals. In this case, that would be down here where equals 2/6 or 1/3. That's something I think I saw a few of y'all do. I don't know if it was y'all, may have been the AB classes or the regular classes. But a lot of people really focused on the work inside the limit, but forget to write limit. That does need to be written until you actually evaluate the limit. But you will need to be able to unpack the question, kind of like the limit derivatives, where they can give you a really ugly limit, but they're not expecting you to answer the limit. They're expecting you to recognize the derivative question inside and then answer that. So they do the same thing with this stuff. You need to be familiar with it enough that you can kind of unpack and look at it and see, okay, this is what the function is. This is the interval, that type stuff. And we're going to work on that by the end of the class period. Yeah. Okay, I want to go ahead and look at number 2. I'm going to go ahead and look at number 2. And number 2, I've already said, is the bad one. Actually, let's do this. Get rid of that page, new page, paste. I'll just do that. Will that work? I don't know. Okay, so number 2. And for these problems, your main formula that you're using, we're doing limit as n goes to infinity of the sum of f of x sub I delta x, and then x, your delta x is your b minus a divided by n. So in this case, that's 2 over n. Your x sub I is where your interval begins, a, plus, and then your delta x times I, which for this problem, that's going to be a is 1 plus, and then 2 over n times I is 2I over n. And so I start by making those substitutions. X sub I gets replaced with that, and the delta x gets replaced with 2 over n. And then we spend a lot of time going over the, goes from 1 to infinity. Then it's just a buttload of algebra after that. Right, so I'm going to be a little bit lazy again. I'm not going to rewrite the limit over and over again. F of x sub I becomes f of 1 plus 2I over n times delta x, which is 2 over n. Step 1. Each individual step is not bad. The problem is there's just like 36 of them before you're done. Right, so first step is fairly straightforward algebra, substitution. Second step, Be careful, but f of that just means we plug that in for the x. So 1 plus 2i over n all squared plus 1. So 1 plus 2i over n squared plus 1. That's f of x, except I replaced the x with whatever x sub I was. The 2 over n I'm just going to leave over here. Now we expand that. How good are we at expanding? If you square that, we'll have 1 squared plus 1 is going to be 2 plus 1 times 2i over n. And I'll have 2 of those. That's what, 4i over n plus 2i over n all squared would be 4i squared over n squared. All of that times 2 over n. My delta x is still just hanging on the outside. What did I do wrong? Very, very possible I made a mistake. I didn't factor it out. That 2 over n is my delta x that's just been staying out there. That's my delta x. We cool out there? Now I'm going to distribute my 2 over n. So I'll have the sum of 2 times 2 over n, which is 4 over n, plus 4i over n times 2 over n is 8i over n squared, plus 8i squared over n cubed. And we are going, and I haven't been writing this part. I'm having a hard time over here. I equals 1 to infinity. Good? I'm going to separate that stuff out so it's not in the way. I'm going to bring this up here. Now that I've gotten rid of all multiplication, there's no more expanding, no more foiling, nothing else inside my summation. I split this into 3 different sigmas. The sum of 4 over n plus the sum of 8i over n squared plus the sum of 8i squared over n cubed. And all of these summations are functions of I. We are plugging numbers in for I. The 4 and the 8s are obviously constants, but as far as the summation is concerned, n is a constant also. N is a variable for the limit, which is going to be addressed later. So because these are all constants, I can pull these constants out of each of the individual summations. And when I rewrite this and break it up, I have the sum of only 4n, and I'm going to take that 4 over n out. And because everything's gone, I'm just going to have a 1. Plus the next sum, I have to leave the I inside the summation, but the 8 over n squared can come out. Plus the next one is the sum of I squared. The I has to stay inside because that's the variable in, as far as the sigma is concerned. 8 over n cubed can come out. And this was really my first objective. I now have 3 different summations that have really nice, clean formulas that can replace those. And I've been lazy. I haven't written the I goes from 1 to infinity. But when I replace those, that's 4 over n times, and that first one, the sum of a constant, n times, as I goes from 1 to infinity, is just 1 time. I feel like I'm messing up somewhere in this. Isn't it the sum as I goes from 1 to n, not 1 to infinity? The infinity is inside the limit. Yeah, so this was a typo. These are supposed to be n's because the n is approaching infinity, which will give you an infinite number of summations. That's there. there. And that gives you an infinite number of rectangles, which is how it becomes an exact area. So satisfying the gods here. So that's one. And so now the sum from the first n constants would just be n, 1 times n, plus, and then I have 8 over n squared. And the sum of I, as I goes from 1 to n, and these are those formulas that are on the top there, n plus 1 over 2. And then I squared is the ugly one that I have a hard time remembering off the top of my head. I think I know it. It's n plus 1, 2n plus 1. Is that right? Over 6, yeah. The top is what I always have a hard time remembering. 2n plus 1 all over 6. I ran out of room. And we are almost done. 2n plus 1. There we go. Good. And then now I'm going to reintroduce my limit. We're doing limit as n goes to infinity of all of this. And when I rewrite it, I'm going to clean up what I can. 4 over n times n is just 4. I can, if I want to, cancel n's here, but it's not that big of a deal to me. So I'm just going to write 8n. N plus 1 over 2n squared. Plus, and then here, 8n, n plus 1, 2n plus 1, all over 6n cubed. And in these problems, you should always finish where you have limits as n goes to infinity and your top degree should equal bottom degree. If you start with a polynomial, which we did, you'll always get top degree equals bottom degree. If you don't, that's a cue that you've messed up somewhere, which sucks. But if you look at all of these, we do have equal degrees on top and bottom. So I have a 4, that's a constant, plus 8n squared over 2n squared. You divide those coefficients, that'd be 8 over 2. Plus, and if I multiplied this one out, I have 8n times 2n. That'd be a 16n cubed and a bunch of other insignificant stuff, leaving you with 16 over 6. And there is your answer. Yeah? Do we feel accomplished? A surge of patriotism welling up inside us? We do have Veterans Day this week. What? No? All right. All right. So we're going to abandon this for just a second. We're going to come back to the Riemann sums. I gave you that multiple choice thing. We're going to look at that in just a little bit. I want to talk to you very quickly about definite integrals. And some of you already know what these are. We have used integrals or antiderivatives. I don't think I've talked to you about the notation. We have been talking about area. So whether we've been actually finding the exact area on an interval like these Riemann sum sigma notation things do, or if it was an estimation of area like the Riemann sums we did Friday. But if you were talking about the area under any function on an interval a to b, that whole sentence can be written in this notation. It's an elongated S, and it's an S for a reason. From A to B, you write f of x, you write a dx, and we'll talk more detail about what the S and the dx and all that stuff means specifically, but for now, I just want you to understand that that notation means you're finding the area under the curve between the squiggle S and the dx. Between the squiggle S and the dx. And you do that through an antiderivative. So that last example we just did, it was, I think I just gave you a function and then I wrote the interval afterwards. It was x squared plus 1. X squared plus 1. And then we were finding the interval, was it 1 to 3? The one we just did? So that notation means find the area under x squared plus 1 from 1 to 3. And you do that by finding antiderivatives. There's a very quick way to get those answers. No different, well, it's similar to when we first learned how to do derivatives. We did this really long, cumbersome limit approach. And then we found out there's a shortcut. Same way with areas. There's that really long limit approach with sigma notation and stuff to get area. Then there's a shortcut. And for the shortcut, you find the antiderivative of your function. What is the antiderivative of x squared plus 1? It would be x cubed over 3 plus x plus c from, and we write a vertical bar, we evaluate that from 1 to 3. You evaluate it by plugging in the top number first. So I'll do 3 cubed over 3 plus 3 plus the c minus, then we plug in the 1. 1 cubed over 3 plus 1 plus c. And then you do the arithmetic to clean it up. That's your shortcut. That's your antiderivative approach for finding the area under a curve. Right. What's going to happen to those c's? Now, when you distribute this negative, the c always cancels if it is a definite integral. If you are evaluating a definite integral, the c will always cancel. So for these problems, you don't need to write the plus c. It's not wrong if you want to, but you don't need to for definite integrals. And then we just do the arithmetic. 3 cubed over 3, that's 27, over 3 is 9, plus 3 is 12, minus 1/3 minus 1. And if you clean that up, it should give you, unless we made a mistake, the exact same value that these fractions give you. Okay. So it's a little bit shorter, just a little bit. But what they'll do is once or twice on the AP exam and in multiple choice situations, they'll ask you questions that are disguised as that summation notation stuff, but they're really wanting you to find the function in the interval and just answer it with a shortcut. So you've got to be able to unpack it. You need to be familiar enough with the process that you can read a problem and figure out what is that hidden question inside, just like we do with limits. Yeah? Yeah? We'll talk more about those definite integrals and stuff tomorrow. Let's look at those multiple choice questions. Let's look at those multiple choice questions. Go away. Where's my... There. By the way, I did, if you're just curious or anxious to do that last example, I need to refresh. I do have the answers here. I also have a video somewhere of me working these out. So there's number 1, there's number 2 that we just did. Apparently that cleans up to 32/3, 4 plus 4 plus 8/3. Yeah, that's what I got. And then there's number 3. So if you want to try the other ones, the other one, there it is, and it's worked out. Let's look at these problems right here. And let's just talk about how we unpack these. And we're just going to work these together. Is that okay? How much time do we have? 8 minutes? So let's look at number 1. And you'll notice on this one, they didn't put it in sigma notation, but they just expanded it out. And we are trying to figure out which of these definite integrals is being addressed with this Riemann sum setup. So I'm looking at this, and the first thing I do is I notice that I'm adding up a whole bunch of stuff here, but I have this 1/50 on the outside. What do you think that 1/50 is representing? That's your change in x. Remember, if your change in x is consistent, when we did Riemann sums, if your delta x was the same throughout, we could factor out that delta x. And then inside the parentheses, we added up all the heights. So there's my delta x. I see a delta x of 1/50. Then on the inside, I'll look at this, and the structure of these numbers tells me what my function is. Now, you could read that two different ways. You could look at it as the square root of, and I'm changing the numerator. You could think of it as the square root of x over 50. And then my x's are going from 1 to 50. But my delta x kind of tells me what we're replacing. This is all in the same structure as the delta x. So what I'm seeing here, this is the square root of numbers, right? So I'm seeing f of x is the square root of x. So I don't like A, I don't like C. The others have the correct function. They all have square root of x. And as far as the limits of integration, as far as the values that we plug in to evaluate, I'm finishing with 50 over 50. What is 50 over 50? That's 1. And we're starting with 1 over 50, but that's really close to 0. So that would be like the right side. If I'm going from 0 to 1 over 50, we're using the right side of that first rectangle. So I'm starting with something that's close to 0. And so I'm looking for 0 to 1. That eliminates E. And so we're now down to B or D. What do you think? Yeah, B doesn't have a 1 over 50. Does it? It does. Delta X is 150. What do you think that delta X is in this? It's your dx. That dx, remember if we take an infinite number of rectangles, the bases become close to 0. No different than in algebra. You did slope with change in y over change in x, and that was when you had a measurable change if you're going from one point to another. But in calculus, we abbreviate that as dy over dx. The delta x and the dx is the calculus adaptation of that delta x. So the delta x is represented right here. Are we good? Weird, huh? It's really weird at first. Let's see if we can do another one. I'm going to skip 2. Let's jump to 3. 3 is very similar to number 1. So same type thing. This time they put it as a limit, as n is going to infinity. But again, I see the 1 over n in front. What do you think that's representing? They're kind of representing the delta x right there, which as far as the integral is concerned, that gets turned into a dx. And then I'll look at the inside of the things I'm adding together. What's my general structure here? What do you think my function, what am I plugging into? I'm plugging into x squareds, right? My delta x, 1 over n, 2 over n, 1 over n. Like I see my delta x inside there. So based on that, I'm already liking D and E. I'm already liking those two. And then I'm trying to figure out what is the first x I'm plugging in and what is the last x I'm plugging in. 1 over n, as n goes to infinity, that's going to approach 0. 3 over n, 3n over n, as n goes to infinity, is going to approach 3. Those are your limits of integration. The 1 over n in front is represented by the dx in the integral. Yeah? Yeah? Once you see these and start to understand how to pick them apart, the multiple choice version of this concept is they're kind of quick. Now, doing it from start to finish, like we did at the beginning of class, that sucks. Sucks bad. Let's look at 2. Can we do this in 2 minutes? Let's look at 2. A lot of words, but this limit right here can be represented in a, right now, that is in the form of f of x sub I delta x. Only they didn't put f, they put the x sub I under a square root. What do you think that means? That means f is the square root of x, right? The delta x is your dx, so really this limit is representing some integral of the square root of x dx. And on what interval are we evaluating the area? If you look here, we're starting at a and we're ending with b. So a to b. And so with that, I have unpacked the limit. Now it has become a definite integral. And I'm going to solve that by doing the antiderivative. So square root of x is x to the 1/2. We do the antiderivative and plug in b and a, and you'll get one of these 5 answers. Yeah? Weird? All right, we did 3 kind of quickly there. Hold on to this. I want to finish the last few problems tomorrow, and I'll take this up for you. I gave y'all at the beginning of class a sheet that talked about properties of definite integrals. That goes with a video I want y'all to watch tonight. So if y'all could watch that and come in tomorrow, we'll hammer the definite integrals a little bit more and just move forward with antiderivative stuff.